All right, let's move on to transcendental functions. So in this video, our objective is to distinguish between families of transcendental functions. We already covered the algebraic ones. Now we're going to cover the exotic ones. So we're going to begin with trigonometric functions, and I know that some of you are fresh out of the battlefields of trigonometry, so my apologies, but we do have to talk about it, right? Trigonometry. Remember that we actually began by thinking about angles. So we have some angle formed by two rays, and that angle, x, remember that we started measuring angles in degrees, so parts of a circle, so 1/360th of a circle, and in radians, where we're talking about 2 pi being a full circle. However, in calculus and beyond, we do not care about degrees. We will never discuss trigonometric functions in degrees. We will only talk about radians, okay? And so when we say x, we say x is a real number, but it is the radian measure of an angle made by the ray passing through zero, zero, and by a ray, sorry, not the ray, and the positive x-axis. So this is our starting point. We're talking about, here's our coordinate plane and some ray. And this angle measure x in radians is the angle that we're talking about. Okay, and so we have 3 classes of trigonometric functions, okay, and we're going to discuss them in tandem. First, we have what we call the trigonometric sinusoids. Okay, so these are, it's not clear that these are functions and that they're well defined everywhere, but we're going to talk about them as if they were. So we have first sine. Everyone knows and loves this one. So we call this sine of x, S-I-N. And it's the signed, meaning it can be positive or negative, height of the point on the unit circle. So in other words, this ray, it intersects the unit circle. Oh no. How do I move that? Maybe if I could move. Nope, that's not what I wanted. Let me just do this. Close enough. And then I don't actually want that. Okay, so that's the unit circle, because it passes through the points 1, 0, 0, 1, etc. It's got a radius of 1 and centered at 0, 0. So sine of x is the signed height of that angle. Then we've got cosine, which we abbreviate as cos x, and that's the signed width of that point. So again, if it's left or right of the y-axis, it will have a different value or a different sign in front. Point on the unit circle. Probably should have made this bigger, this graph anyway. So that distance, whether it's positive or negative, is our cosine of that angle. Next, we've got our trigonometric ratios. So these are tangent, which we abbreviate as tan, and that's going to be the ratio sine of x over cosine of x. Similarly, we have cotangent, which we abbreviate cot x, and that's just the opposite. It's cosine of x divided by sine of x. All right, provided cosine of x is not equal to 0 in the first case, and provided sine of x is not equal to 0 in the second case. Right, can't divide it by 0. Okay, third class of trigonometric functions. The trigonometric reciprocals. These are secant, which we abbreviate as sec x, is 1 over cosine of x. Again, provided cosine of x is not equal to 0. And lastly, cosecant, which we abbreviate as CSC, given that cos was already taken, of x is equal to 1 over sine of x. Again, provided sine of x is not equal to 0. All right, so notice that there are exactly 6 of these functions that we're interested in. Are there more? There are. But here's the important thing. Even though we're talking about them in terms of the unit circle, and of course this is going to be important, so I'm going to get to that in a second. Even though we're talking about it in terms of the unit circle, ultimately x in radian measure, which is unitless, and our standard angles are, so in other words, the ones that we're mostly interested in are in the interval 0, 2 pi, and not including 2 pi because these functions cycle back. They're what we call periodic. We'll get to that in a second, okay? Again, and I'm going to write this in big block letters, no degree measure. This is so incredibly important because if you have your calculator set in degrees, it messes everything up. We're only talking about radian measure. All right, now that we have that out of the way, let's do a quick refresher of the unit circle. Unit circle, what you love to hate and hate to love. So, we know that the unit circle, I keep doing that, sorry. The unit circle just refers to the circle of radius 1, centered at the origin. So let's hope I get this big enough. And that looks just about centered at 0. Okay, so we have the points 1, 0, 0, 1, 0, negative 1, and negative 1, 0. Okay. Each angle that we determine here can be represented on the unit circle. And the ones that we typically are interested in are the ones ranging from radian measure 0 ranging all the way up to 2 pi. And then it starts over again, right? it is imperative that you memorize the unit circle. I know that was discussed in trig. You had to memorize the unit circle, and then some people will say, don't memorize the unit circle. You know, you'll always have a quick reference, and while it's true that you'll always have a quick reference, memorizing the unit circle at this point, at this level of your education, is about as essential as having to memorize the alphabet, unfortunately. It just comes up so often, right? So while, yes, you can quickly refer back to a unit circle, there's no shame in that, it will be faster and much more efficient for you to actually memorize this, okay? But I will say this, memorize just quadrant 1 and then the tips and tricks to get you the rest of the quadrants. Because in calculus, we're going to be referring mostly to positive angles, or we'll be talking about certain quadrants only. And so having to memorize the whole thing is not necessarily necessary. But we are going to talk about some essential angles here. So the first quadrant ranges from 0 to pi over 2, right? So Q1 and if you go right for middle, right, we're talking about the angle pi over 4. Pi over 4. Then that point on the unit circle is the point root 2 over 2, comma root 2 over 2. And there's some standard arguments that we use in trig to figure out that is true, right? So that one is easy enough to remember, root 2 over root 2. Then we talk about two more angles that are essential here. The first being pi over 6. So a sixth of this half pi, which is really a 12th of the whole circle. And that point on the unit circle is root 3 over 2, comma 1/2. Lastly, we talk about pi over 3. And that point on the unit circle is the point 1/2, comma root 3 over 2. That's this point. Don't want to make it too cluttered, okay? So some quick ways to remember this. Remember that the crucial angles here are 0, pi over 6, pi over 4, pi over 3, and pi over 2, okay? And you can use all sorts of symmetry to figure out what quadrant 1, quadrant 3, and quadrant 4 are going to give you, okay? But really importantly, you can identify a pattern here where for the y coordinates, you're talking about 1/2. So root 1 over 2, root 2 over 2, and root 3 over 2. So the argument inside the radicand in the numerator goes up by 1. And then conversely, for the x coordinates, the radicand starts at 3, and then 2, and then 1. Not too bad, right? Okay. So, importantly, here are some other important things to remember. The first coordinate, the x-coordinate of that angle, is cosine of x. The second coordinate is sine of x. Okay? So in other words, what we just found here was setting up a nice little table where if we're talking about our angle x, and we want to find the first the sine value, and then the cosine value, then all the other trig values. It's as simple as looking at the x and y coordinates of that angle. So we have 0, pi over 6, pi over 4, pi over 3, and pi over 2. So for sine, we start at 0, and then we're slowly going up. So 1/2, then root 2 over 2, then root 3 over 2, and then lastly 1. Because you'll notice this is an increasing pattern. Increasing. Cosine, on the other hand, you start at 1, and it's going backwards. It's root 3 over 2, then root 2 over 2, then 1/2, and then 0. So this is decreasing. And lastly, if we're talking about tangent, remember the tangent is sine over cosine. So it's defined for 0, and it's 0. For pi over 6, it's 1 over root 3, which is root 3 over 3. Then pi over 4, root 2 over 2 divided by root 2 over 2, it's the same thing, so that's 1. And then lastly, root 3, because that's root 3 over 1. And at pi over 2, it's undefined, because that involves division by 0. And you can do that to fill out the rest of the trigonometric functions of that angle. And so where we're headed to then is we're going to discuss the actual functions that we get here. So the trigonometric functions properly are functions of a real variable, and we're going to graph them. So in this video, we're just going to finish off by talking about the sinusoids, and then in the next video, we're going to talk about the other two subfamilies. So let's talk about the sinusoids. So remember, the general form, and we're gonna graph the parent functions. So the general form, though, is f of t equals capital A sine of omega t minus phi. This is a lot, but this comes from physics and standard. Capital A is the amplitude of the sinusoid. Omega is the angular velocity. We'll relate what these mean in terms of transforming a function later. And phi is what we call the phase shift. Phi if you're in a fraternity. And similarly, we have g of t equals a cosine of omega t minus phi. But we'll quickly see that this is actually redundant because we can find both sine and cosine as special forms of just the first one. So this one is the really important function to remember, and the second one is a special case of it. And then the parents, of course, are f of t equals sine of t. I'm using t here instead of x, but we could use x. And in fact, I will for now. F of x equals sine of x, and g of x equals cosine of x. So let's just examine the graphs of the parents. Okay, so graphs. So I'm going to graph first sine. I always do this. And for these functions, we're going to just draw one part of the function. because it is periodic, so it repeats. But importantly, some of the points that we already kind of pointed out are, for instance, 0, 0. We have pi over 2, 1. And pi over 4, root 2 over 2. So it looks something like this. And then beyond that, now we're talking about other quadrants. And so interestingly, what happens is we actually get a mirror image of that across pi over 2. So that when we come back down to pi, sine is 0. And then we get another flipping where we have between pi and 3 pi over 2, negative root 2 over 2. And then at 3 pi over 2, we get negative 1. And then again, negative root 2 over 2 when we're halfway between 3 pi over 2 and 2 pi. And lastly, we come back up to 0. So the graph of this function looks like this, roughly, and then it repeats. So, oops, that doesn't look, that looks better. Okay, so again, let's recap. Our function is increasing up until pi over 2. So this is pi over 4, root 2 over 2. Here's 0, 0. Here's pi over 2, 1. These are all points on the graph. And then after pi over 2, we're decreasing. So at 3 pi over 4, we have root 2 over 2 again. And then we hit pi 0. Then we're in negative territory. So for 5 pi over 4, we have negative root 2 over 2. Then at root 3 pi over 2, we have negative 1. And then at 7 pi over 4, we hit negative root 2 over 2 again. And lastly, 2 pi gives us 0 as a y coordinate. Okay, that's a lot, right? But if you can remember these points, you have the essential shape of sine of x. Okay, now let's do cosine. Jesus, I always do this. Okay, sorry. Now we've got cosine. So again, I'm going to fill in negative 1 and 1. And we're again going to go from pi over 2, pi, 3 pi over 2, up to 2 pi. Okay. This one's different because cosine, remember, starts from 1 and then it comes back down. So it hits some essential points here. I'm going to label right now. So 0, 1, pi over 2, 0. Pi negative 1, 3 pi over 2, 0, and 2 pi 1. And we can fill in some intermediate points like it hits pi over 4, root 2 over 2. Then it will hit 3 pi over 4, negative root 2 over 2, and 5 pi over 4, negative root 2 over 2, and how about 7 pi over 4, root 2 over 2. And now we can trace the essential shape of this graph, which looks something like this. And it's periodic as well, so we should fill in the dashed line so it repeats forever, right? Okay, moment of truth. What are the essential properties of the sinusoids? So number 1, essentially, very important. These functions are what we call 2 pi periodic. Actually, I think this is the color that you use for definitions. 2 pi periodic. This means literally for all angles x, sine of x plus 2 pi equals sine of x, and cosine of x plus 2 pi equals cosine of x. That means the y values repeat every 2 pi. So we get the same fundamental shape every 2 pi. Parity / symmetry. Sine is an odd function. Cosine is an even function. You can kind of see it a little bit from the graphs themselves, right? Sine appears to have this symmetry where if you rotate it about 0, 0, it should look like the same graph. It'll make more sense if I actually, fill in the rest of the graph. Looks something like this, right? Similarly, if I can fill in the rest of this, it does look like cosine must be even, right? Because it has that symmetry across the y-axis. What about the, x-intercepts? Well, for sine, these are located at every integer multiple of pi. So where k is -2, -1, 0, 1, 2, etc. Right? As for cosine, and you can see this from the graph of sine, right? So every full integer multiple of pi, we are crossing the x-axis. As for cosine, we're only at the half integer steps, and only the odd half integer steps. So what we'll call that is the location is x equals 2k plus 1 times pi over 2, where again k is -2, -1, 0, 1, ... Okay, so these are the locations of the x-intercepts, not necessarily the values themselves. Remember, x-intercepts are points. They both have unrestricted domain, so all real numbers, and they both have a range -1 to 1. As we'll see when we modify these functions, we can change the range to be anything we want. All right, so stay tuned for another video where we talk about the ratios and the